All right, let's pull back the curtain on one of the most powerful concepts in all of computer science, the graph. It's the hidden blueprint behind pretty much everything you do online. And seriously, once you see it, you're going to start seeing it everywhere.
Okay, so think about this for a second. What on earth could your Facebook friends, the GPS in your car, and the entire internet possibly have in common? On the surface, it seems like absolutely nothing, right? Well, it turns out they're all built on the exact same and kind of surprisingly simple blueprint.
So, here's our game plan. We'll start with what connects us all. Then we'll learn the language of graphs. After that, we'll get into how to store those connections, see where they are in the real world, and finish up with a super handy developer toolkit. Let's do it.
All right, first up, what is this fundamental thing that connects pretty much everything? We're talking about the graph, and it's basically the ultimate model for understanding any kind of network you can imagine.
At its core, the definition is, well, it's beautifully simple. A graph is just a collection of points. We call them nodes or vertices, and these points are linked together by connections, which we call edges. That's literally it, just nodes and edges.
And this is where it really clicks for a lot of people. Just think of a map, right? The cities, those are your nodes. The roads connecting them, those are the edges. Or let's take a social network. Every single person is a node, and the friendship between two people, that's the edge. See? Pretty intuitive.
Okay, so to really get our hands dirty with graphs, we've got to learn the lingo. So in this next part, we're going to break down the key terms and look at the different personalities that graphs can have.
First up, the vertex, or node. This is the main character in our story, you know? It's the thing. In that social network example, you are a vertex. Your best friend? They're another vertex. Each person is just a single point in the network.
And the edge, well, that's just the relationship between two of those vertices. It's literally the line that connects the dots. So if you and your friend are connected on the network, that connection, that friendship itself, is the edge.
Now this is where it gets interesting, because edges can have rules. On one hand, you have an undirected graph. Here, relationships are mutual, like a two-way street. Think about Facebook friends. If you're friends with someone, they're friends with you. But then you have directed graphs. Here, the connection has a direction. Think of Twitter or Instagram. You can follow someone, but that doesn't mean they have to follow you back. The relationship only goes one way.
And we can add even more detail. An unweighted graph is simple. You're either friends or you're not. A simple yes or no. But with a weighted graph, each connection has a value or a cost. Now, going back to our city map, this is a total game changer. The weight of a road could be the distance in miles, or maybe the travel time in minutes. And this one little idea, adding a weight, is what lets something like your GPS find the absolute fastest route, not just any route.
Okay, so this is all great in theory, but how do we actually, write this in code? Let's get practical and talk about how we translate this cool concept into something a computer can actually understand and use.
So yeah, the big question is, how do we tell a computer about this graph? How do we store it? It really boils down to two main ways of doing it.
First up in the ring, we have the adjacency matrix. Just picture a simple grid, like a spreadsheet or a 2D array. If you have 5 nodes, you create a 5x5 grid. You just put a 1 in the cell if node I is connected to node J, and a 0 if it's not. Super straightforward, and it makes checking for one specific connection incredibly fast.
And in the other corner, we have the adjacency list. Now, instead of one giant grid for the whole graph, each node just keeps its own little list of who it's directly connected to. So node A might have a list that just says B and D. That's it. It's a way more focused approach. So let's have the showdown, matrix versus list. The matrix is a speed demon for one thing, checking if two specific nodes are connected. But, and this is a big but, its weakness is memory. If you have, say, 1,000 nodes, but they're not all connected to each other, you're still creating a grid with 1,000,000 cells, and most of them will just be 0. It's super wasteful. The list, though, it's the champion of memory efficiency. It only stores the connections that actually exist, which makes it perfect for those big, sparse graphs, which turns out is what most real-world networks look like.
And because of that, for most real-world problems, we have a clear winner. Since things like social networks or the web are massive, but most things aren't connected to everything else, the adjacency list is almost always the go-to choice. It's just way more practical.
Okay, so we know what they are and how to build them in code. Now for the fun part, let's look at where these things are hiding in plain sight. And while we're at it, we'll clear up a common point of confusion. What's the deal with graphs versus trees?
I mean it when I say they're everywhere. That people you may know feature on Facebook? Pure graph algorithm. Google Maps finding you the fastest way to get coffee? Yup, that's a weighted graph algorithm. The internet itself, just a giant web of sites linking to other sites, is a massive directed graph. Heck, even when you compile your code, there's often a dependency graph working behind the scenes.
So, about that tree question, people ask this all the time. Isn't a tree just a graph? And yeah, it is. A tree is just a very specific, more restrictive type of graph. The key rule for a tree is no cycles. You can't start at one point, follow the branches, and loop back to where you started. It's got that strict parent-child structure. Graphs are the Wild West. They can have cycles all over the place. Nodes can connect to anything. It's a flexible web. So remember this. All trees are graphs, but not all graphs are trees.
All right, let's wrap this up with a practical developer toolkit. Think of this as your cheat sheet for when you actually start coding this stuff up yourself.
Here's the quick and dirty guide. Is your graph dense, meaning tons of connections everywhere? A matrix could work. Do you need lightning-fast checks for one specific edge over and over? Again, matrix might be a friend. But for pretty much everything else, especially if your graph is sparse or you're going to be running algorithms like BFS or DFS, you're going to want an adjacency list. It's just the better all-rounder.
And before you go, let's talk about a few classic rookie mistakes to avoid. Number 1, forgetting to add an edge in both directions for an undirected graph. Remember, it's a two-way street. Also, watch out for those off-by-1 errors with your vertex numbering. Are you 0-indexed or 1-indexed? And please don't try to use a matrix on a huge, sparse graph. Your memory will not thank you. And finally, always ask yourself if edge weights matter. If they do, and you ignore them, you're going to get the wrong answer.
So, what's the big takeaway? You now have the foundation. You know what a graph is, you can speak the language, and you know the pros and cons of how to build one. You've basically just drawn the map. The next big adventure is learning how to explore that map, using powerful algorithms like BFS and DFS. So now that you can see all these hidden connections, what are you going to build with them?